Welcome to lecture 35. You have to bear with me. I'm a little bit under the weather, but we'll try to power through this. News of the day is there's a really cool research, NSF-funded research, in which they have found that perhaps they've found memory faster and more efficient than flash. And that could change the entire dynamics of our memory hierarchy, that flash is now inserting itself somewhere between cache and normal RAM. In terms of instant-on laptops, you power it on, and because you're using a flash-based drive, it's much faster than using a normal drive, et cetera, et cetera. Ferroelectric materials, which are used in smart cards, are lower power, higher efficiency, and higher speed, and also non-volatile. That's the key thing, right? DRAM is volatile. You turn the power off, it loses power, but flash isn't volatile, so it keeps its values of zeros and ones even when the power's out, and that's the idea. It's pretty cool. So it's Cilium, what's the name of it? I can't even read what the slide says, but they're strontium. Yeah, I don't know what it is. I don't even know what it's doing, but it's doing some pretty cool stuff. To be honest, I don't understand the the material science properties of it, but it's pretty cool stuff. I also have some news today. You should give a shout out to Mohammed Sleem from Texas A&M, who's watching remotely. Hello, Mohammed. Also, Project 4 will not have face-to-face grading. We had said that was what the last lab was going to be, a lot of face-to-face grading. Turns out we have tremendously efficient and effective auto-graders. So you've been given a third of all the auto-graders. All the auto-graders is 22 tests, and you've been given 8 of them. So that should test most of your code. That said, you want to test more than just the 8. Your code may still have bugs, even though it passes your 8, so make sure you do your own testing as well. We have a hidden set of, I guess what it is, 14 more that we're going to pound on it. And once you take the sum of those 8 plus our 14, that's going to be basically your grade. So that's how we've done this Project 4 in the past, so no worries about having to sign up. That's a lot of overhead and logistical support for readers and TAs and you guys. Don't worry about that. It means that next week you have no lab. It also means the following week there is no lab either, because that was going to be face-to-face grading, and now there's none at all. We're going to make that lab just makeup. So if you're missing any lab, check off. Just do come that time. So it'll be kind of a soft, easy time for the TAs. Most of you won't have to come, but if you need to check off, come on in. Or you want to have some more special time with the TA, do that as well. And there was a hitch with Project 2 submissions. We ran out of disk space. Turns out when you have all the data files to do the MapReduce stuff, that actually caused the instructional machines to choke, and we lost some set of submissions. But the nice thing is you didn't lose the actual data files. We just lost the submission process. So we might need you to resubmit them, which shouldn't be with no penalty, obviously. Just go back to your original files, click resubmit, and that should just work fine. So you're going to see it. Check the Piazza post. Is that right? Check the Piazza post for who needs to do that submission. Okay? Good stuff. So let's jump right in. So we were talking about virtual memory, the benefits, the wonders of it, and what it buys us. We now know that virtual memory is, the real benefit is that you can have protection from other users, and this wonderful abstraction that your program owns all 4 GB, and you don't need to worry about anything else of how it's managed. It's just, you think of your 4 GB as all living resident, as a wonderful abstraction. You don't need to worry about it from the programming side, anything else. You saw the page table was the translation, which keeps track of actually where those pages are. Are they resident? Are they not? Are they on disk? This is true not only for each user, as it says, but also for each process. Every process you run has its own page table. That could be a lot of space overall. The TLB, we saw that each time you access the page table, it cost us a memory hit, as well as the memory hit of trying to get the data. That was 2 memory hits, and that's a problem. So we want to try to cache our page table, and TLB, another word for TLB is page table cache. We saw that as a way to make that page table look up really fast. Okay? So, and the key thing is spatial locality was true. We saw for caches as well as for VMs. Spatial locality and temporal locality are both true for both of those models. Okay? That's all review. So here is the page table. I've got a virtual address, which has a page number and an offset. We saw that before in my eJournal. Here's my page table. This now is an index into that, and now I have a physical memory address. And that physical memory address is probably going to be smaller than my virtual address. If I have at least 4 GB, maybe that is the same width. But if I don't have 4 GB of physical RAM, that's probably fewer bits than 32 there. The other nice thing about this same model is you can now upgrade to a 64-bit system. And Macs and I think Windows are all, the new versions are all 64-bit. So you can now run in a 64-bit address space. Anybody have an idea how much memory you can get to with 64 bits? Who knows? 64 to the 64 is 16 exabytes. That's a lot of RAM. Remember what exa is? Remember the whole thing? Well, who remembers one of the things? The KMG thing. Who remembers a fun one? Kissing, Mel, what's the one? I don't know. What's that? Kissing Mel Gibson, so gets the gig out. Okay, keep going. So gig is like 3. Go ahead. Teddy, 4. Pendergrass, 5. Exclaimed. That's 2 to the 60th. That's a lot, folks, right? 1,000 times more than a petabyte, which is 1,000 times more than a terabyte. That's a lot, folks, okay? So it's nice to live in 64 address space because what? What if I only have 4 gigs, 16 gigs, 32 gigs of real RAM? Does it matter? No. It'll swap the pages I'm actually using resident, and I can still think in the world of owning to the 64 address space. That's awesome if you're dealing with massive data sets. Only the actual part of the code, the actual part of the data you're using, that gets loaded resident, and it just swaps it back to disk. So as long as you have a ton of disk, it just works. It's really amazing. So this works for 32-bit virtual and smaller, as well as 64-bit virtual and however much you can how much you can afford to spend. Okay? So we noticed that there was a page table base register, which allows us within one cycle to change which page table we want. And that's a really important thing. We saw that as well. One level of indirection is a powerful thing. This is also, we saw this picture, but we didn't do the details of what happens. All of the arrows here are covered with all the bullets. So the first thing is, quick, you do a load word. I want to go to memory. Let's go. And I say, no, that was the old days where I just go to memory and I grab it and I bring it back. It's a lot more complicated now. Why? Number 1, I check the TLB. What's the purpose of that? Well, I want to make the memory find out exactly where that page is fast. So if it's a hit, first the virtual address comes out of the processor. Load word, this memory address, 32 bits wide. Okay? That immediate value goes into the TLB. I look up, I say, give me the thing. Is it there? Are you there? And that TLB is a cache organized any way any cache is. It can be direct mapped, set associative, and fully associative. Okay? So if it's a hit, I got it. And out comes a physical address. If it's a miss, I then have to check the page table, which I know is in memory. So I had to take one memory hit if it was a miss. Okay? If it's a page table hit, what does a page table hit means? Resident. It means that page is resident. It means it's valid, okay? If it's a page table miss, otherwise known as a page fault, because it's the page's fault, remember that model? The page is not my fault, it's the page's fault. Then, here's this page fault, which means I have to fetch that from memory and bring it back in. I also have to return the translation to the TLB. I have to update the particular page table to say it's now valid, here's where it is, here's where it lives in physical RAM, as well as updating my TLB so the next time I come in with the same relative, if I ask for any other memory access within that same page, my TLB is going to have it and it'll be instantaneous, which is one cycle, right? We got that. Then, out to hold that thing came out a physical address, which usually, as I said, is smaller than the virtual address. So then I say, let's check the cache. The cache is the first thing I checked. And I drew a big circle around this PA because before you were always thinking of you're checking your virtual address, your 32 bits against your cache. And for the first time you saw on Wednesday, you're not anymore. You're checking your physical address against the cache, which probably is a smaller bit width, and therefore your tag is going to be smaller. All this is review, by the way, but here's more details. So now the physical address comes in, you check the cache, T, I, and O. Offset is for where you are in that block. I is the index into your particular row in your cache, and the tag is the tag you check. If you have a hit, yay, cache hit. I save an access to memory. It's a miss, then I have to go to memory, grab that particular whole block, bring that block into my cache. This is like review, right? This is like I've done this before in the cache days. Bring that to my cache, update it. Do I need to now tell the TLB or translation anything? No. At the stage of the cache hit or miss, I'm just updating the cache or not. So it's 2 separate pieces of that. So in the best case, in the worst case, I'm taking 2 memory accesses. Actually, in the worst case, it's a lot. What is the worst case given this picture here? Let's just say it's the worst possible case. where I say, oh, I need the data right now, but all of a sudden, Murphy's Law is hitting me, and what's the worst thing, given this picture and this kind of algorithm, can happen? And describe for me the setup. What would be the worst case in terms of doing something? Yes, Rohan. There's a lot of steps here. Give me the setup. Describe the setup. Describe a world for me in which the worst case is about to happen. Go. Okay, so even before that, even before that, that was a load word you're going to give me, right? Right? No, worse than that. There's worse than Rohan's suggestion. Give me worse than that. Yes, go. Worse. Before that, give me a setup. I need a setup. There are two memory accesses when you look at the five-stage pipeline. Remember the two memory accesses? Instruction and data. Everyone so far has said about data. Tell me about instruction. It's going to be bad, folks. When I say bad, I mean really bad. Go. I could jump, but let's say no jump. Let's just make it easy. What if my last instruction I accessed was the last word in a page? How about that? Let's pause and just reflect on that. I happen to be storing all of my memory, by the way, it's divided into pages, right? Including my program, which in theory is loaded into RAM. But maybe not. Maybe the data you've accessed is pushing it out. And so those pages, which were part of your instruction, part of the code part, have been kicked out. How about that? So the instruction before now is the last word. It's an add or something, which is the last word in that whole page. What does PC say? PC equals PC plus. Are we dead today? What happened? Come on, give me some love, people. Where's my folks? Come on. PC equals PC plus 4, right? That sends me to the PC to point to a new page. Where is that page? On disk. It's not resident. So the worst possible thing that happens is I now have to look up where that is. I don't know where it is. How do I know where that page is? All I have is 32 bits from a PC. So I say, it's time to now fetch the next instruction. So guess what? This whole process happens for the instruction too. Not just for the data. This happens for the instruction too. Because I'm making a memory access to find out what's that next guy, which happens to be a load word. But it happens to live on a page that doesn't even live resident memory. I'm starting to swagger because I'm feeling good about how bad this can be, right? I'm going to make this as bad as possible. This is Murphy coming to you at all levels. So what happens? You go for that instruction. Is it in the TLB? No. This is the worst case, right? Not in the TLB, because I haven't accessed it in recent time. But TLB is the recent guide you've accessed. You haven't accessed it either before or recently. I go to the translation. What does translation say? I look it up. It says, on disk. How does it tell me it's on disk? Valid bit set to 0. Therefore, it's on disk. Oh my gosh. Even to get the next instruction, I have to now deal with this. Now, guess what? Worst case. What does my memory look like? Full, right? Worst case, full. Full of what? Dirty pages. I'm making it as bad as I possibly can. So even to get to my next instruction, I have to do what? I got to take a page, the last one there, and kick it out. So I'm going to where? Jupyter. To take this page that was stank and dirty and bring it back into memory. Or bring it back into disk. Sorry. Bring it from memory. Here. I'll grab it from here, a stank, dirty page. I'm going to Sacramento. I'll go back and put it in disk. Okay. Long wait. Now, imagine long wait. Okay. I come back. Phew. I came back from Sacramento. I just ran. I'm so excited. I knocked the microphone off. Okay. So, I came back from Sacramento. I'm ready to go. What's the next thing I have to do? Oh, wait, I forgot. While I was there, I was supposed to get the page you wanted with the load word, right? Okay, so I go back to Sacramento. This is a forgetful system. So I forget that I was supposed to grab a page while you're there. I grab the page of your code that has your next instruction, which is hopefully a load word. I bring that in. So I went to Sacramento once, dropped something off, which is writing the dirty page back. I brought it back in. When I bring it back in, what do I have to do? Update my TLB. Okay? So my TLB is now good. So my TLB has it, and I also have to update the page table by changing the valid bit to be valid 1. Now, I read it. It says, load word. I say, oh no, not another memory access. Well, what do we do? Load word, some address, 32 bits wide. What do I go now? TLB. Worst case? Not there. Go to my page table. What does it say? Not there. Invalid. So, got to go grab some page that was old. What's the worst case? It's dirty. So now I have to write a page all the way back to disk in Sacramento again, and now bring it back in. Now, if I bring a page back in, how about this cache and memory thing? That's probably not going to be there too. So that's a miss. I have to go to memory and get it. Okay. That was really painful. Can you imagine how painful that was? Okay. The other thing about this is, I'll save it till later. I'm going to say something about save it till later. So this is actually a little bit more details of how this works. This is a TLB. Check this out. Okay. Blink. There. This puts it a little bit more perspective. If you have a TLB, it's a cache. A cache based on what? A cache based on your VPN, right? You go and look it up by VPN. The page table was the raw VPN. But it turns out that if you're looking about a cache, you think about the cache in the same way. You have an index and a tag. And that index and the tag are part of what the VPN was. Why? This is why I usually lose the class right now. This is how I always lose the class. Because this page is really complicated. Because A, there are 2 offsets, which I drew as 2 different colors to indicate the 2 different offsets. Green offset is what? And for those colorblind, the top offset is green. So the green offset is what? That's the page offset. What's the pink offset on the bottom right? That's the cache in the block. Okay, so two same words, same thing. Oh no, I have a tag down here and I have a tag up there. What's the TLB tag? That's the tag to make sure I'm not talking about another page that happens to map to the same index. Remember TIO? There's a T and an I. And this is the same TI that you saw before, except that I'm talking about a tag which is the TLB tag as part of the VPN. All those words still feel like a mouthful of like, what? I can't keep track of all these things. But in fact, this is just a little bit more complication. I'm teaching you nothing new here, just that if you're going to have your TLB be anything but fully associative, then you got to have a tag there. Actually, then you got to have an index there. If it's fully associative, no index. But you need a tag nevertheless, even if it is fully associative, to keep track of the most recent stuff. Would you probably have a fully associative TLB? Who says yes? Hands up. Who says no? Hands up. Okay. So most people know wins. Why no? Back. Somebody in the back of the room. Give me some love in the back of the room. Come on. Why wouldn't you have a fully associative TLB? Yeah, go ahead. Behind one hand. Did you have your hand up? No. The additional data structure to keep track of who's there, who's the most recent guys, is going to defeat my one cycle access. I want one cycle access to this TLB, right? I don't want to have to go to memory. And I cannot manage all the data structures to make a fully associative TLB in one cycle. I can't update that stuff. I can do that if I'm going to save going to disk, but I can't do it if I'm going to save going to memory, because all that is basically a lot of really memory access to kind of keep track of all my pointers, to keep track of my sorted list of that stuff. Okay? So that's the big picture. Questions about this? This big picture is it. All I'm introducing new is that the tag index is how you figure out where in the TLB you go, which is just like the cache days. If you were confused in the cache days, you're more so now because there's more things. But if you got the cache days, you got the TIO from the olden days, then maybe you can say, oh, it's the same thing I saw before. Okay? Now this physical address is a different width than my virtual address.
I have the PP and offset don't necessarily map to the tag index and offset. This offset might be wider, smaller, right? Probably this offset is bigger because you're talking about a much larger page than a block size. So this probably is going to be smaller. This index is however many different sets you're going to be mapping to. Direct map, it's the number of rows. If it's two-way set associative, it's that number divided by 2. And I have a tag to tell me whether that part of it is there or not. So this is really cool. This is a really important diagram, and circle this kind of on your notes as like an important diagram to understand as I ask you exam questions. This guy is really important. Start there if you're having questions on your exam. So inside the TLB, what's a row look like? In the normal cache, it was easy, right? It was tag, maybe valid, maybe dirty if it was write back, and then data, right? It was all the rows of all the rest of the block. Here, I've got my tag, okay? I've got my dirty, my valid bits, because I might want to have some saw that before. Access rights, we talked about the access rights being an important thing. This reference field, which if I'm going to have an LRU-based page table, this reference will help me determine that guy. And this would be true for my page table as well. And a physical page number. That's my data. What I'm getting out of my TLB is that second column, my physical page number, right? In comes the virtual page number, out comes the physical page number. That's the purpose of the page table. That's the purpose of the TLB, which is just a faster access to the page table. Okay? So what if it's not in the TLB? We kind of went through the worst case. If it's not in the TLB, you could have two options to that. I don't think I've ever mentioned that before. So the hardware could take the job. It's the hardware's job to load the page from disk and do that work. Or the hardware could say it's the OS's job. And that's the way that we think of it. That's the way that MIPS does it. So that's the way you should think of it. If it's not there, if it's a page fault, then the hardware traps the OS. The OS says, it's the OS's job, which is the hardware knows nothing about it. A trap, Mike's going to talk about when we talk about I/O basics on Monday. And the trap is going to be able to say, a trap is a synchronous exception. So that means, asynchronous means it'll happen, blink, it'll happen right. It won't happen in the middle of a clock, it'll happen at the clock at the next kind of time. It'll jump right in, but it'll jump right in the middle of one of when I say in the middle, it'll complete atomically, an instruction will complete, and then rather than go to the next one, PC+4 to the next one, it'll say, OS is taking charge. You'll leave, OS will do some work, and you come back right where you were, and you won't even know that you took a break. It's like you kind of froze, and then somebody goes and rearranges all the furniture, and then we keep going. It's like, wait, how'd the furniture get rearranged? Well, the OS took care of that. So the OS has the job of moving it. It's not your job to do that. So here's the cool part. If the data needs to be brought from Jupyter back to memory, there's this cool idea. Who's heard of a DMA before? Hands up. Like 4. Okay. DMA stands for Direct Memory Access, and it's really cool. Two things. One is, it's a way to write data from a disk to memory. That's cool thing number one. Okay? Here's a whole chunk from disk, just write it to memory. Just copies it over. Abstractly, think of it that way. The cool thing number two is, the CPU isn't involved. That's awesome. Even if you have one core, one processor, one core, a DMA does not involve the CPU. CPU is happily getting work done over here, but that transfer is still happening while the CPU is over here not working on that process, because that process probably had a page fault. The DMA will happen, make the transfer for you. Abstractly, someone else is taking a charge for you. The CPU doesn't need to be the guy, okay, copy byte, write byte, copy byte, write byte. Not the CPU's job. Isn't that cool? So you can actually have the disk spinning, and the CPU is happily going over here computing something else. That's really powerful, really effective, and all of a sudden you've got no loss. When you have a page fault, the CPU just keeps chugging along getting your work done, which is awesome. Okay? And when you switch back, by the way, when you switch, when you switch back to that task, the CPU is like, oh wait, hey, there it is. Like the CPU kind of goes, I'm going for the data, and then all of a sudden slow motion, page fault. I swap out, I'm kind of frozen, right? The process is frozen. You save the state of that process. Let the DMA happen. It can swap. Even if you have one core and one CPU, it swaps over to something else that needs the attention, the OS maybe, or another program running. By the time it comes back, it's there. So from the point of view of the program, it never needs to worry about that. That was option 2. And while it was still getting work done, the DMA was just happening without the CPU's knowledge. Love that. Really, really powerful stuff. So, blink. If you don't have enough memory, buy more memory. No, I'm joking. But if you have a problem that requires this much memory and you ended up being stuck, the solution is always to buy more memory. Okay? That was like, how do you fix the capacity problem of a cache? That's what this is. A capacity miss of a cache means the cache isn't big enough. Well, make the cache bigger. Well, I can't. It's in the hardware. It's, somebody put it on the board. But remember, virtual memory is like memory is a cache for the disk. So if you're having trouble, you want to solve the capacity misses in your virtual memory system, buy more memory. That's the way to make your system faster. Like, wait, what? Did he just say that buying more memory makes my system faster? The clock's the same way, the CPI is the same, the ISA is the same. How is it faster? Class? How is it faster? Fewer page faults, fewer times to visit disk, which is to go to Jupyter. All those things, all the problems of like having to have the swap out and the dirty and get it out there, all those worst cases, go down to like almost never if you can fit it all in space, or if you can have more of it than before. So buying memory actually makes your programs faster, makes your system feel faster. So if I'm going to buy a new laptop, I say, what's the max RAM? That's what I want. I don't want to have to deal with, well, I could be faster. Like, if you actually, people don't realize this. People are going to the Mac store and they're saying, well, I only have this much money. Should I buy the 3 gigahertz or the 2.97? I'll buy the 3, but I'll save money by not putting memory into it. Are you kidding me? Are you kidding me? Buy the slowest CPU, but max out your RAM. You will have way better performance on average case stuff where you have lots of things loaded and lots of memory stuff, which is what I do. I have a QuickTime and a Photoshop and a thing and a rendering over here in Premiere. I'm a big, heavy memory user. So I'm somebody who would much rather have a little bit less CPU speed, but all the memory I can have and not have to worry about disk access. Huge. Another way to make it faster. Faster disk. Get flash drives, get flash drives rather than normal rotation, and we'll see that also next week of how disks work. Disks are way slower than flash drives, so get a flash drive, and don't pay through the nose for the 4 terabyte drive, but get a reasonable sized drive, have that be your major boot up drive that your disk swap space is being used for. Like when you're actually taking and writing to disk, that's using your swap space, have that swap space on the fastest drive you can. Okay, so what happens in the worst case? In the worst case, I have multiple programs all competing for my little bit of RAM that I have, and all the system is doing is literally thrashing. It's just taking pages and back, and there's no computation being able to get done anymore. It's literally spending all of its time swapping processes, moving page table, moving pointers to the different pages, trying to give somebody some love, but in fact, every single I did this. I'm going to show you an example of how to kill your system, and I have an example right here. It's pretty cool. So, thrashing is what happens when basically your system is unresponsive and all it's doing is just moving pages back and forth because it can't survive. It's like underwater. It's like having a mortgage you can't pay. Okay, so let's do some clicker questions, and then I'll actually show you my demo where I kill my system. Okay, so let's go here. Ready? Go. 40-bit virtual address, 16 kilobyte page. I hope I didn't put the answers. I might have put the answers in the slides. Don't look at them if I did. Just be nice and try to not look. I might have put them in there. 36-bit physical address. Those aren't real numbers, but why not? You should be able to answer this question in this weird world from Mars of this 40 and 36 rather than your normal 32 and smaller. What's the number of bits in the virtual page number / page offset, comma, physical page number, page offset? This is the easiest one. It gets much harder after this. But let's see if we can sleep through 3 questions in a row to actually kind of ask you some numbers. This is the kind of question we usually ask at the start of the question of virtual memory. This is the easier questions. Then it gets a lot harder about what happens in this particular case of this code, what happens, and you'll see that in the exam as well. So let's go. We have about 120, I'm going to guess, so if everybody clicks in, so we'll see how that works. Here's 114. By the way, I have found that the students who are really sharp in being able to go from 2 to the xy to a number, like 2 to the 64, 16 exa something, those students are really fast at these kind of things. If you're still kind of not sure what 2 to the 9th is, then you're going to be slow, like, what's 2 to the 9th again? Da, da, da. But if you're really sharp in that, then you can do this much faster. So I would say now's the time, if you haven't memorized those tables, memorize those tables. Like 2 to the 1x is a killa, kibby, something, right? Like ki. 2 to the 20 something is a maybe, that kind of thing. All right? So let's pause this one and see how you did. Since I have 3 questions I want to show you my demo, I won't allow discussion here. But let's see how you did. Okay, so that's that one. And I get blink and C. Well done, C. Look at this nice distribution here. Look at that. Interesting. Okay, so give some love to C. I'll hide this now. Okay, try not to look at the answer, which is in your handout, I think. The next one here. So now, 40-bit virtual address, 36-bit physical address. Now, let's talk about your TLB now. 2-way set associative TLB, which has 512 entries. That is what you can consider your virtual address looking like this. It has a TLB tag, a TLB index, and a page offset. That's your virtual address up top. In the entry for a TLB, we're going to have a valid bit, a dirty bit, access control, which is 2 bits, a virtual page number, which is actually what you care about, and the physical page number. Virtual page number is not in that entry. I don't know why that says. That's an error. That shouldn't say virtual page numbers in there. Physical page number is there. I don't know. That shouldn't say virtual page number. That's a bug in the slide. I'm going to change that slide. There's no virtual page number in that entry. There. That's much better. Do this there and go back here. There. Maybe I should say TLB tag. That has to be in there too. Okay. So, I should click start maybe. Yoink. Okay. Maybe you figured it out already. The bottom line of its block says 18.858. So I don't think these kind of questions are so indicative of real deep understanding. This is just, can you remember where the bits go? And da-da-da. The deep understanding is, here's some code. What happens? How can I fix the code? How can I optimize it for fewest page faults? That kind of thing. That's the part that really is showing you understand this stuff. This is just kind of counting bits, which is important, but not the critical piece. I think is the critical piece of that. In real world, nobody's going to ask you this in Amazon or Google. My code is slow, my disk is thrashing, what can you do? And then you come and say, see this memory access is messing up the page, has more page faults if you do this, fewer page faults, you optimize it for reduced disk access. Okay, about 130, and, oh wow, keep people kicking in, great. Up to almost 140, and I'll stop now. Good. Okay, so let's see how you did here. Okay. How are we doing for time? I still have time. Good. I want to show you this really cool demo. Bink display. So again, you're centered on the C. That's 2, the C thing. And it's again a C. Well done for that. So I'll give you love to the C. Let's see why it is. After I click that one, hide. So if I have 512 lines, but that's 2-way set associative, I only have 256 different sets. That means 8 bits for the index. The remainder, 14, 8, and 18 have to add to 40. So that's how you get the 18. So now you know 18 and 8. And now you know it's either C or E, basically. And between C or E, how many is it? Well, physical page number is 22. As we saw before, you have to kind of remember that one. The tag is 18, which copies down. This tag has to be in that line. Once you know what the tag is, you have to store the tag into that line to test where it is, whether you're the right tag or not. And V and D are 1 bit and access 2 bits. So all those bits add together to 44, and there's your C. Okay? So, last one. We're doing pretty well. And I'll just start this while I describe what the question is. So now, I've got my physical address. Now it's time to go to cache. We're putting the whole thing together now, folks. Now I'm going to cache. My cache happens to be two-way set associative, 64 kilobyte data cache, 64 byte blocks. Then I have the physical address, is 36 bits, divided by tag, index, and offset. Remember, TIO in Spanish is uncle. Uncle Dan is, remember that? So TIO, data cache entry, valid, dirty, cache tag, plus how many bits of data? So that's the question. So the number of bits in the data cache tag /index /offset /entry. And the bottom line says 21,96535. And then we're going to see a demo which crashes my machine. All right, I'm so excited. So give me 140. Go on back. And stop that. 140, good, that's my number. See how you did here. Okay. And display. And so most people are on the E. Let's see if that worked here. So I'm counting 21 bits, 9. So 21.9 works because, again, it's two-way set associative, so it's not 10 bits, it's 9 bits. So 21.9, I'm either D or E. And the cache data is 64 bytes, which is 512 bits. So that's a lot of bits. We're talking about bits here, I guess, on this, just to be clear on that, not bytes. So this is a lot. This entry is much wider. That's a lot of bits. Well, yes, that's a lot wider on that side, which is good. Okay? So I get E, and if I can display, I give E some love. Excellent. Okay. Who wants to see my machine die? Yes. All right. So I will, and there's E. So there's a summary, but I'm not going to kill my machine. Here we go. So I'm going to quit all the programs because I want to show you that everybody else. Well, if I'm going to do that, then this is annoying. I have to say yes to this. If I'm going to do that, let me show you at least the last slide. I put some bonus slides in there to talk about general caching. Here's some general stuff, summary, then I can quit PowerPoint, and we'll just live in purely terminal and activity monitor. The cool thing, you say, Dan, what did you learn this week? Hey, student. Hey, mom, this is what I learned this week. I learned that. Here's the summary. This is the one-page summary, one-sheet summary of what you learned all week. One is the user's abstraction. This is the most powerful, I think this is one of the most important abstractions that you've learned in this class, to be honest, is that there's a lie that we were kind of propagating until this week, which was, yeah, you own all 4 Gibby. It's all yours. But you don't really own all 4 Gibby. But the abstraction is you still can think that way. It's okay. That's an okay lie. It's a beautiful abstraction. And it's contiguous. You own 4 Gibby, that's contiguous. No way. You're broken up to pages, and those are in disk and all strewn about memory. It's cool, but you think of it as being contiguous. You just sweep through an array. It just works because of this indirection, because of this virtual memory system. Okay? By the way, the name of this, by the way, is called demand paging, as compared to branch and bound. So you start from some set address. Everything starts from 0, infinitely large, and I say infinitely large in the sense of being 4 Gibby. And it's the only running program. All those are lies. All those are lies. In reality, it's not contiguous. You start wherever the memory is. It's a finite size, and memory programs are running out of time. Beautiful. I love those two. That's like the definition of abstraction. You don't need to know that stuff. You can think in that world above, and it just works. Here's what it provides. Protection sharing is critical. And the implementation is, again, divided into pages. The OS controls that. Memory is a cache for the disk, and the TLB is a cache for the page table. Okay? So that's virtual memory. And with 10 minutes left, here is this demo that I did this morning. Let's see if I can get it to work. Okay, save that, quit it. So now I have nothing running except for terminal. Now, this guy, I don't know why he's so dark. You know why that's so dark? It's the strangest thing. All this does, you can't, isn't it crazy? Like, it's just a terminal window. I can maybe make it, let me make a new terminal window. Maybe I can, here we go. C and code and VM and more, VM test.c. There. So that was easy. If I Emacs it, will it color code it nicely? Let's see if that works. Give me some love. There we go. So I don't know what's happening with this window, but I don't like it anymore. Okay. So here's my code. Page size is 4096 on Macs, and that was something that Mike showed. You can verify what that is, and that's kind of cool. But you can verify that with code, and if I move this away, move this over here, there's this wonderful system query, sys control hardware, and then you can more it to look at other things, but I can also grep for page. So if I copy this guy, and I copy this, and I Control-Z this, and I say syscontrol grep for page, and I don't know, hardware page size 4096. So you should all try this on your system. So I figured 4096, I'll just hard-code that guy into my machine. I probably shouldn't have hard-coded it, but I did. So let's think of it there. So that's my page size. Number of pages, I have 400,000 pages. I tried a bigger number, and I got a malloc error. Like, my system won't allow me to malloc, like, 2 GB. It was really annoying. First of all, the argument to malloc was treated as an integer. So when I asked for exactly 2 to the 31, it wasn't so happy. So you know that the biggest number in an int is 2 to the 31 minus 1. So it was saying, you can't do it. You have this addition, this page times that number of pages was a number that it couldn't store in the argument to malloc. So I said, okay, well, I'll make it minus 1. And then that error didn't cause, but it says malloc won't succeed anymore. So I had to keep bringing it down until I finally had the biggest chunk I could grab at one chunk. Now, I might be able to have multiple ones of these guys. So I might be able to actually get more memory in multiple successive calls to malloc, but that was 400,000 pages is about the biggest one before without causing an error. So here's what I do. This is very simple code. I print out all the steps. Like 1, I'm before malloc of 1 page, before I do anything, right? Then I malloc 1 page, I say after malloc of 1 page, but before malloc of some huge number of pages. Then I malloc this huge thing. Then I say after malloc of these pages, before touching them all. And this is a little for loop that just touches them all. It sets, one character in each page to 0. It's the worst possible thing I can do, right? Touches each page, writes to it, sets a character to 0. It started with garbage, right? Set one of those characters to 0. Then I say, after touching all pages, before looping. And now, 5 says looping, and I just say, do the same thing. I just loop, and I keep touching all those pages. This is the shortest code that's going to make the most painful memory access ever, right? This is much more efficient than touching each byte. It's like touching each page, jumping by pages. Because you notice, my pointer is pointer I times page. So it's exactly, 0, then 4096, then 91, what's the other thing? Whatever it is, right? 8192, etc. Okay? So let's try it. So here's what's cool. Ready? This is the cool part. So now I made an animation. So watch this one. So let me show you this first. Desktop. VM 400K, and I took those screenshots of, let's see if this works. Does it keep it in memory? 0, 1, 2, 3, 4, 5. Okay. So I took a screenshot, and I can even do, look at that. I can even do that, okay? So on the top is my status of the running guide. The middle guy is me looking at swap file to see if it actually needs to have more space on the disk to swap stuff out. And it doesn't so far. So I only have one swap file, which is 64 megs. Okay, I have a nice 64 meg swap file. And this is Activity Monitor, which tells me what's running. Whoops, it's actually animating. That's pretty cool. So now, look here, before malloc, it's not even running. Sorry. 0 is nothing. Nothing here. I should click. that. Is paused? I want to be paused, yeah. So before anything happens, no process running named VM test. It's called VM test, right? Next frame. I now have before malloc of page 1, and I keep, this is a clear and recheck. So again, nothing really changed. Still one swap file. VM test is running, but look how much memory is being used. 17 megs of virtual memory, and real memory is only some number 100 of K, which is pretty small, okay? Now, after malloc of one page, before malloc of the whole thing, of like a couple of gigs, right? One point something gig. Still virtual memory small, and real memory small. Ready? Bink. Now I've malloced it, but I haven't touched them all. So virtual memory is 1.1 meg, which is not that big, and real memory is small. So now watch this one. Now I have touched all those pages. My virtual memory is 1.54. My real memory is 1.54. Okay? And what's cool is if I move this, can I show, how do I move this guy? Notice how, what's also cool about this is, it's killing me. All the information is right behind, that's so annoying. Look at this guy right here. So look at my free space, 3 gigs. Now I'll go back, okay? I started with 4 gigs, 4.86. And as I keep going, 4.86, and then 3.33. So the system says, oh, you're using up your free space is now much smaller, okay? And now I can see that 1.54 gigs. Now watch this, ready? I keep going, and now the same thing here, and this is now looping. Nothing changed between the looping and the touched it once. Because I've just touched it once, it already kind of gave me the footprint. Now what I haven't shown you is the following. Here's the coolest part, ready? This is how I bring my system to the knees, to its knees. I quit preview. I close Finder. I hide this terminal, and I watch this. I have several different versions of this guy, okay? Named, this guy basically is going to just grab and actually use like 1.34 gigs of space. I have 8 gigs free. This is a pretty big machine. So I have a couple of these terminal windows, which are all set to run. Notice how, first of all, notice how responsive my system is. I'm grabbing the windows, it's responding to it, I'm listening, there's no disk spinning, okay? Now, let's just go through, first of all, let's see whether it released my space. Ooh, it still used one of them. So it actually grabbed one swap file that it still needed. Before I showed you only one swap file, it actually makes another one. So it's actually increasing its memory requirement. Now watch this, ready? Here we go. VM test, this is my main one. Okay, now here we go. There's 4, and now I'm saying go. Now watch this guy down here. 8 gigs, okay? And now it's looping. So the CPU is going to kick up as well, okay? And now watch my free space. Oops, now only 4. Interesting. Let's go over here. VM test 3. Enter, 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 okay? Okay, watch what happens there. Watch my green guy go away. Free space 2, okay? And he's looping. And remember, it's supposed to print loop every time it hits hits every page, it says the word loop. This guy's getting a lot of action because he's getting a lot of the loops printed. This guy's getting any time. He's in the same state. 5 looping, but he hasn't yet looped because this guy over here is demanding all the time. The CPU is just spending the entire time hitting that. And notice, both of my cores are now maxed out. Let's go over here. Launch one more. Ready? Okay. So now, okay, look at that, there's green, okay, and now one more, let's just for fun, whoops, oh no, he's getting some attention, the top guy's getting some attention, here's 4, okay, there's that one, and now just for fun, let's hit this. Still only 2 swap files. No more free space. See the guy here? See the green? Gone. Now we're at the worst possible case. I am now thrashing. I have no free space available, and now all 4 programs I'm running are all simultaneously trying to grab negative space, right? Whatever I have. So all of them are trying to grab them all at the same time. Oh, look, swap file. And notice the swap file is twice as big as the last one. That's 128 megs. The next time I actually need more, it'll go to 256 megs. It keeps doubling it to say, like, rather than just keep going linear things, if you want more, I'll double it, what you had last time. My machine is now completely thrashing. I have no chance to get any kind of responsiveness. Here I do, but this guy is some love. This guy is killing me. He hasn't even got to looping phase. So I haven't even actually gotten to all of the machines in the loop stage yet, because they're still, they have to say the word loop before this guy's had enough attention to finish it all. So this machine is completely thrashed, no green. My free space is 8 megs. There's a little sliver you can't see down there. 8 megs, right? My disk space is also cool. Those swap files cost me some disk space. So my disk space started much bigger, and I can just show here. How about this one? Uh-oh. Look how slow. Look how slow, look how slow. Hey, look at that. Look at my swap file. And my disk used to be much bigger than that, but those swap files cost me a lot. So as I keep going, I'm losing my disk through this, and this is really cool. Oh, look at that! Swap file 5! Isn't this great? And this guy still hasn't gotten attention. This guy here, look at this. This guy here, where's my cursor? Oh, no cursor. Oh, the cursor. At some point, this thing actually doesn't even respond to my mouse even. It's just awesome. Just takes 4 of these worst-case systems to have the whole thing grind to a halt in my particular system. Probably takes 1 or 2 for your smaller memory systems. Okay. Guys, have a great weekend, folks. Hope that was a good demo.